So I'm Jacob, and as he just said, we'll talk about Cosmos-Xenna and Cosmos-Curate. So brief outline. First, we'll just explain what Cosmos is, and then go over an intro into Cosmos-Xenna, and then some lessons we've learned while developing Cosmos-Xenna and just running large pipelines at scale. Finally, we'll talk about Cosmos-Curate. So Cosmos is a platform for physical AI at NVIDIA. So we make generative world foundational models, and then we also have accelerated data processing and curation pipelines for video and other physical AI stuff. The intent is for people to use Cosmos to accelerate development of physical AI for autonomous vehicles, robots, etc. So essentially, we're building like base models for physical AI applications. Next, we'll talk about Cosmos-Xenna. So what is Xenna? So it's an open source library that we use on Cosmos to run our data pipelines. So right now it's open sourced, but needs additional work before it's ready for wide adoption. It's mostly used internally today, but with enough interest, we can convince people to like increase our external support. So like Ray Data, it's a library, not a framework. It's relatively self-contained and portable. So here we have an example of a Xenna pipeline. So on the left, you can see sort of the general layout of the pipeline. So we have multiple stages. First, we download the data, then we do pre-processing on CPU, and then we run inference on GPU, and then we upload the stage. So this is just an example pipeline. You can have pipelines with like many stages. Some of ours have like 20 stages. And then on the right, you can see the code for that pipeline, or at least part of the code for that pipeline. And bottom right, maybe a little hard to see there, but there's a specification for the pipeline. It's relatively structured. So, says you do download stage, then pre-processing stage, caption stage, writer stage. And then on the top right, you can see the definition for the caption stage. So some things to point out there, each stage can have separate batch size. And right here, when you're specifying these things, you're essentially specifying the properties of each actor. So each actor is receiving a certain batch size. Each actor has a certain required resources. And here we made it a little parameterizable so that you can, based on the TP size of the model, you can change the number of CPUs and GPUs allocated to that actor. In addition, we have an SPMD mode, which is, for people not aware, it stands for single program multiple data. It's the way that Torch runs programs. And so in Xenna, you can have actors that span multiple GPUs and multiple nodes as well, if you're using this SPMD mode. Finally, there's setup and process data methods. So the setup is run once whenever the actor is created, and that's where you would load the weights onto the GPU, et cetera. And then process data is the thing that's called for each task. And so you can see this looks like roughly like Ray Data, and we can talk about the lineage of all of this. Some differences with Ray Data is that we don't do the sort of block stuff that Ray Data does under the hood. You're literally just passing Python objects between the stages. We more explicitly support this sort of like multi-node, multi-GPU via this SPMD mode of operation, which I know that Ray Data does support multi-node stuff through the LLM API. And is a little bit more structured. Oh, and the big difference between what we do on Xenna and Ray Data is that we don't handle like shuffles and reduces or anything like this. It's really built for these sort of like cascaded inference pipelines, what you see here. It's like one stage feeds into the next. You don't have like shuffle stages or anything like that in the middle. So the history here is that 3 years ago, we were running these pipelines and we were using Dask. We found that it was pretty inefficient and hard to run, hard to diagnose, et cetera. We switched to Ray Data, which was much better than Dask, but at the time we ran into a lot of memory back pressure efficiency issues with Ray Data. I've actually tested Ray Data a little bit recently and found that I think they've done a much better job with back pressure, although we haven't done like large scale comparative tests recently. At the time, we ended up forking Ray Data and modified the scheduler to fix some of the issues that we found. And then eventually, enough sort of like technical debt built up that we decided to just like build our own thing that's heavily inspired by Ray Data and called it Xenna. We spent the last 2 years improving it, and we've used it to run hundreds of GPU years worth of compute via our data pipelines. We've open sourced it a few months ago. primarily because it's needed by other open source products. So just to talk a little bit about our problem statement, and this will be pretty similar to anyone that's doing like large multimodal data pipelines. But basically, our data sets are petabytes of video, images, 3Ds, et cetera. We annotate the data primarily using deep learning models. So we run captioning, scene detection, aesthetic scoring. The topology, as I spoke about before, is very simple. It's just maps, no reduces, no shuffles, nothing like that. The pipelines, a single pipeline can take, for us, like a month worth of cluster time to complete. And then the developers running these pipelines are primarily researchers with some software engineers. We are occupying entire clusters or large portion of clusters at a time, and we're operating on relatively bare bones infrastructure. And we can talk a little bit more about the challenging cluster infrastructure that we have here. So on the left, you can see what I would consider like sort of like ideal cluster infrastructure, where like you have your data and your compute all within a single region. In our reality, we actually have our data typically in like San Jose, and our clusters are just all around the world. And so that introduces some challenges, as you could imagine. So one is that we have high latency connections between our data and compute. Separate things that we have to deal with our infrastructure is that we have a small cluster local storage, and we don't have jobs that auto-scale. So essentially, we're given fairly bare bones infrastructure support, and we have to figure out how to make that work for our clusters. So next, I'll just talk about the lessons we've learned in developing Cosmos-Xenna, as well as just running these large pipelines at scale. And as we'll also talk a little bit about the design decisions that have come from those lessons learned. So first thing, and I know a lot of talks have talked about this at the conference so far, is that streaming execution is super important. So if you come from a more traditional data processing world, you're probably used to doing like batch-wise sort of execution, where if you have multiple stages in your pipeline, you wait for one stage to fully complete, you write that to some intermediate storage, and then you spin up the next stage. And that's a pretty bad way of utilizing heterogeneous resources, in particular, in our case, CPUs and GPUs. So instead, like RAID data, we use streaming execution here. So you can run your CPUs and your GPUs at the same time, and so you can get much higher utilization of heterogeneous resources. Some other benefits of doing it this way is that you don't need large cluster local storage between each stage, or rather on each cluster, to store your intermediate outputs. That's helpful for us because we aren't necessarily guaranteed to have large cluster local storage. You can also get partial results from your pipeline quickly, so it's fairly helpful for testing pipelines. And as you can see, this is all like inspired by RAID Data's blog posts on streaming versus batch, which is listed there. Another lesson learned is that like streaming execution is pretty hard, or at least like streaming execution this way is pretty hard. So basically, for us, we end up having very large samples. So we're processing videos or large images. Those can be very large, and so if you're storing everything or you're queuing everything up in memory, you need to be very careful about how much stuff you queue up. So we do that in Xenna, so we're really careful about back pressure, very careful about how much stuff we queue up. And a sort of like corollary to that is that if you're being very careful about your back pressure and how you're queuing things, you need to be very careful to balance your pipelines. And what I mean by that is that if you have too many actors in a very fast stage and not enough actors in a very slow stage, you'll end up throttling somewhere in your pipeline. And here we have like a little pictorial example of that, where on the left you have a very balanced pipeline where you have a fast stage, a slow stage, a medium stage, and they all have like the appropriate level or appropriate number of actors such that the throughput of each stage is equal. So your overall, at steady state, your overall pipeline throughput is equal. And on the right, you have a unbalanced pipeline where you have too many workers in your fast stage and not enough on your slow stage. And so your subsequent stages will end up throttled, and your throughput of the overall pipeline will be bad, and you'll get bad GPU utilization and stuff. So another lesson learned is like actually maybe streaming to object storage or like cloud storage is a much better way to do this. So instead of doing like what other frameworks do, or like what Xenna does at the moment, where we store intermediate outputs in memory, we should probably be storing them to cloud storage. And so you can still do the streaming thing where you get good utilization of heterogeneous resources, but cloud storage is essentially unbounded, so you don't have all these queuing and balancing issues. Oh, and I should also, taking a step back, I should talk about, like, we spent a lot of work in Xenna to make sure that the balancing works fairly well. And so, there's probably 3,000 lines of Python and Rust to figure out this balancing problem. And then the the downsides of this thing that I'm proposing here of like using cloud storage as an intermediate is that, number one, you need an in-region object store for that to work. And then there's additional complexity because you need to make sure that you're efficiently downloading and uploading from that cloud storage, and then you also have more object storage cost. Some other lessons we've learned is that when you're running these pipelines at very large scale, just getting the artifacts to the jobs can be pretty troublesome. So, you might have like many terabytes of artifacts, and what I'm talking about here is like model weights, Python environments, etc. And so you need to be careful about how you get those artifacts to the job. And in particular, in our case, where our object storage is located in potentially a different region than our clusters, we need to be very careful about it. So in Xenna, we've built a P2P artifact download distribution system, kind of like a Dragonfly for Docker images, if you guys seen that. But basically, instead of each node downloading stuff from object store independently, they will work together. And this is a simplified representation, but basically, you download from object store once, and then each node is grabbing from other nodes to grab those artifacts. And then finally, this is actually a little out of scope for Xenna, but I think it's important to talk about. You should think pretty carefully about how you do your data lake. So for us, we sort of just decided that we're going to just throw Postgres at it. So when we're storing the results of our pipelines, we do this thing where pipelines write to Postgres, and then that data ends up getting synced to Delta Lake, and then another pipeline will read from Delta Lake. And this is complex, it doesn't scale well, and the sync is pretty hard to maintain. What we're looking to move forward to in the future is to use something like Lance. I think it's sort of potentially a good middle ground between like relational databases like Postgres and more simple like file-based stuff like web data sets. And they're actually doing a talk right now, but yeah, very interesting thing to look up. And next I'll give Hao. Give it to Hao.
Sure. So another lesson we have learned is by running a lot of like data curation in production is that observability is very important. So one of the key challenge here, like if we compare to a typical model training job, which basically every node run the same thing every 10 seconds or so. But here the situation is very different, right? You will have X pipeline stages that are running at the same time, which include like Y different models, right? Then for each of the GPU actor, we also have a lot of CPU actors that is designed to do pre-processing and post-processing, for example, downloading, uploading, or doing decoding of the videos. Right? Also, each stage will have a very number of actors because of the auto-balancing. We keep tuning that. And those actors are spreading on a different node. And also another point, because we run so many different actors, so I actually have to disable the Ray task and Ray actor metrics coming from Ray, otherwise they blow up my Prometheus instance. So given that, some of the example debugging experience we have faced is, for example, a system womb happened, like one of the node goes out of memory, it's down. But if I look at the log, right, maybe roughly 200 actors were running on that node. Then how do I figure out which stage I should look into, right? Then a similar situation happens when you find your overall utilization is low, but there are several different models running on these GPUs, each taking some number of GPUs. So how should I figure out which model the inference to look into? So given that, we have built a set of pipeline-specific metrics into Cosmos-Xenna. So the primary goal of this set of metrics is that we want to link the hardware matrix or the system matrix with this logical stage. And also be able to aggregate these metrics based on the stage. For example, I want to get a per stage aggregate usage of CPU. I mean, they may coming from all different process on different node, but I want an aggregated view. And also the system memory, again, aggregated per stage. And then another, like the second goal we want to achieve is like we need to expose a set of metrics, kind of describe the internal state of Cosmos-Xenna or the orchestration layer of Cosmos-Xenna. For example, we wanted the per stage queuing state and actor pull state such that we can figure out potentially which stage is a bottleneck. Right? So here is a snapshot of like a fraction of the dashboard we are able to populate. So this is automatic, right? When you run stuff with Cosmos-Xenna, then we ship an open source dashboard that will get automatically populated. Okay, so to kind of close on Cosmos-Xenna, we want to really highlight the reliability and the performance aspect of it. So the kind of the reason we are confident in this is because Cosmos-Xenna has a very high mileage. It's iterated across a large volume of data and also diverse data. And also we have worked with many different customers and partners with their data. So with that iteration process, right, many optimizations have baked into the implementation. I'll give one example. One of the customers we work with, they have a lot of videos, and so their kind of cloud storage bucket have a mix of like very small videos, 30 megabyte, 2-minute videos, but also very big videos, like 10 gigabyte, 5-hour videos, right? Then if these are all flowing to the pipeline, initially we will like wound pretty badly, but over time we have many optimization baked into the implementation such that now we're able to handle this kind of extreme cases. Also over time, we have built a lot of tunable parameters that are now exposed to possibly handle new situations. For example, if I want to make the auto-balancing algorithm to react faster or slower, or be a little sticky, there'll be a parameter to do that. Or like for whatever reason, you want a certain stage to have more resource such that it will never be a bottleneck. We have over-provisioning factor to tune that. Or even like, let's say your implementation have a very tricky, hard to debug, slow memory leak, that memory keeps going, we can handle that. Then I can transparently restart the actor periodically, so you don't need to worry about that. So next, we will be talking about Cosmos-Curate. So it is another open source project that is a data pipeline framework built on top of Xenna. Right? So this open source Cosmos-Curate it provides first several reference pipelines for video processing and also AV data processing. Also, it provides a CLI launcher that can help you run, like first build the image, and also launch on like Docker locally or onto a Slurm cluster or onto some Kubernetes-based platform. Also, it includes a lot of recipes and utilities for like developing new data pipelines, right? Then we also have a kind of separate from the open source offering, we also have a managed service deployed on DGS Cloud, such that like for customers want onboard, have a trial, it will be very easy. So if you have a lot of video data, you want to get a sense of how this behaves, please reach out to us. So here, kind of describe the video curation pipeline as a reference we provide to the, along with Cosmos-Curate. So let's say you have a lot of internet videos that you want to turn them into a trainable data set. So we have 3 pipelines here. So the first one is called split, filter, annotate. So, sorry. So it will split these long videos semantically into short clips. right, based on like the short change. And then you can filter them out, filter some of the videos out based on, for example, motion and A-stack score. And then for the remaining good video clips, you can annotate with like VRM caption and also the embedding. Like the embedding can be used for search and also later, like the next stage, semantic deduplication, because often these videos have a lot of duplicates, so we can run the semantic deduplication pipeline to get rid of those duplicates based on the video embedding. And in the end, you can run a sharding and a dataset generation that will generate a web dataset that is kind of ready to train. Okay. Oh, maybe an additional thing that we didn't talk about the AV pipelines here, but recently NVIDIA released a white paper that we are working with. We had a demo together with Uber that is using Cosmos-Curate to curate the AV data from Uber, such that we can fine-tune a video generation model to generate like these rare scenarios of like airport pickup, airport drop-off. Okay, so to conclude, so NVIDIA Cosmos team have open sourced Cosmos-Xenna, which is a Python library that powers petabyte scale data processing internally. And then also Cosmos-Curate, which is a data pipeline framework for building pipelines with Cosmos-Xenna. Oh, I should mention that, so if you want to use Cosmos-Xenna, Cosmos-Curate can be an example to like how you want to build your stuff using Cosmos-Xenna, even if you don't really want to use Cosmos-Curate, right? It's a good example of using Cosmos-Xenna. Okay, that concludes our talk. Thank you. And the Cosmos team is hiring, so if you're interested, please reach out to us.
All right, thank you. Thank you, Jacob and Hao. If you have a question, you can raise your hand.
Hi, great work. So one question is like, I saw you have built extensive observability for the pipeline, and you also mentioned like maybe the data size or basically for even for different roles, they will have different workloads. So in this case, do you also rewrite the data placement logic in Ray? Basically like Ray data also has some like placement strategies you can use, but do you rewrite them for further optimization?
The locality stuff, I think. Oh, yeah. Sure, I think we do relatively similar logic to Ray data. If I'm hearing this right, basically like you have one stage and you need to get the data to the next stage. So when we're scheduling stuff, we prioritize optimizing or prioritize sending stuff to the same stage, of course. I think there's additional optimizations that you've done, but generally we try to schedule within the node, although that's not always like possible. Does that answer your question?
Oh yeah, that is like some locality, but also sometimes like different roles, maybe they will generate data, different roles, they may generate different amounts of data, and then some of them, if you, in the same batch, if you still map it to the next batch, maybe not ideal sometimes.
Oh, I see. Yeah, maybe I can talk about that. Basically, between the stages, it just gets thrown into a giant pool, and then it will get batched from there. And I think we definitely do some locality stuff there as well. But I guess maybe to get more at the intent of the question, we're really not trying to be like Spark or like we're not. Basically, Xenna is optimized for these sort of pipelines that are doing GPU inference, and so like the low level, how you're moving data around is typically less important, although it's big data, so you still have to be careful about it, than it would be like on more like traditional ETL type pipelines.
Cool. Thank you.
Thank you.
Thank you for the talk. When you talked about the peer-to-peer transfer in between nodes for data from the object store, how do you do that? Like, how do you do the peer-to-peer part?
Yeah, it should be a little bit clear here. So this is basically just for artifact downloads. That's like the stuff that you need to start up the job. So model weights. For us, it's con environments. We have like a system that's kind of on top of Xenna, not in Xenna. But we do basically the same thing as like Dragonfly or whatever, where basically there's a main scheduler that's like orchestrating all of the nodes, and it's making sure that things only ever get downloaded once from the object store, and then they're sent from the nodes that have it to the nodes that need it. So it's like kind of like BitTorrent with an addition that you're pulling from the object store.
Thank you very much for the talk. I have a somewhat wishful question. Is there any chance you're going to merge this back into Ray data and that we have the best of both worlds?
I think it's pretty infeasible right now. I think one of the reasons that we ended up splitting off initially was it was hard to fork Ray data and then add these features because Ray data has a lot of complexity going on because it's trying to do more things. You know, Ray data has a ton of stuff in it. Like specifically, I think Ray data is trying to do like this sort of distributed inference thing, as well as like more like Spark type workflows with like reduces, scatters, all of these things. And so it was very hard for us to modify Ray data to make what we needed happen. Yeah, if that answers your question. I think it's probably still pretty hard to modify. That being said, the Ray data folks, I know they worked a lot on like back pressure and some of the scheduling stuff, which was our primary reason for starting this. For us internally, I doubt we could go back to Ray data because we have so much tweaks and stuff here for our big pipelines. Yeah.
Maybe a little more additional information on that. So I think I remember before we kind of open source it or formally, we did have a meeting with the NScale folks that also like when we just open sourced before we broadcast it, we send that to NScale folks first. They are definitely at that time was interested in certain aspect of Xenna, so it's possibly they integrate some of the good features here into Ray data.
Yeah, thank you for the talk. Could you go more in detail about like how you guys schedule actors, like what resource management you guys do, and possible like bottleneck detection?
Yeah, so basically it all comes down to this auto-scaling thing. So, you know, we're just starting up a bunch of, we have a certain amount of stages, and then each stage has a certain amount of actors in it. And for us, like the actual sort of like scheduling, like which piece of data goes to which piece, like which actor is not that hard. You have to be aware of locality, but other than that, it's not that hard. The hard part is balancing those stages as we talked about here. And so like essentially you want to maximize, well, okay, so what we do actually is that we measure sort of like the ideal performance of each actor. So we measure like from the time it got the data to the time that it like finished processing the data, how long that took. And we use that to make an estimation of the throughput of that actor and build that up to a throughput of the stage. And then once you have that throughput information, you can figure out how to balance the stages. That's like sort of the high level algorithm, but in reality, it's like it's way more complex than that because you need to make sure that you always have like one stage or one actor per stage so that you have at least some throughput going through it. And then you also need to over allocate some stages just to be a little bit more robust to like changes in throughput. And then finally, there's also sort of like a GPU placement problem here that Ray has like sort of simple heuristic to solve, and then we did something more complex. So there's actually like a bin packing problem like stuck in here as well.
I see. So when you first start those pipelines, are you like what initial parameters do you use then? Because if you're calculating like the throughput, then you need to be it needs to be running at first, right?
Yeah. So in practice, like what happens is that it's pretty slow to start up. So if you were looking, well, so we auto scale every X minutes or something to get enough like information about the throughput of the stages. And so for the first 3 minutes by default before it auto scales, it'll be relatively inefficient because you'll have sort of like a random number of actors in each stage. And then once it's gathered enough information, well, really it's just every 3 minutes it'll auto scale from there. you could there's an extension to this. Like we should definitely allow users to sort of put in a hint at how fast each actor is or each stage is, and then you could get like a snappier startup.
Thank you.
Cool. We actually at time, so let's thank our speaker one more time.